Okay, back to our regular program. We've got static program analysis for security. Over to you.
All right, hi guys, my name is Zain. My talk is going to be on static program analysis for security. This is a really interesting area for me, and this is an area of active research. And we will also see towards the end some applications of this that you could use in your projects. So this is the overview. First, we're going to talk about what static program analysis is and why we would want it. And then we're going to do a bit of discrete maths just because we need sort of that foundation in order to talk about what we're going to call, what we're going to see later, which is data flow analysis, which is a specific form of static program analysis. And then towards the end, we will look at CodeQL, which is a tool that's used in industry for this sort of thing. So you guys are probably going to be familiar with dynamic analysis, things like unit testing and fuzzing. So these are just tests that you write on a limited number of different inputs. So you test different edge cases. Problem with this is that it often reveals the presence of errors, but you can't really guarantee that your code does not contain any bugs. And just because you have 100% test coverage doesn't mean that it's not, you don't have any bugs. It just means that you covered all of the branches, but how good your test is that's up for debate. And then once you find a bug, you write a regressive test and make sure that never happens again. But how do you make sure that, how do you write tests that prevent future bugs? So that's where we want static program analysis. So this is can you analyze code without actually executing it? And this is really nice for you to sort of provide some guarantees about the behavior of your program. So I found this tweet really interesting. So just going to leave it up for a bit. But I guess it shows that first, you can never trust QA engineers. And second, you can never anticipate anything that happens in the real world. You could test all of the edge cases. But the first time you have a real customer, a real user using your program, it's going to go wrong. So we're going to look at data flow analysis, which is a particular form of static analysis that examines how data moves through a program. This is useful because in security, you're always going to be asking the question, does untrusted data ever reach an unsafe function? So does your user input ever get to a point where it could influence the program's behavior in a malicious or just in a bad way? So before we get into that, here's some revision of discrete maths. So a partial order is a binary relation that is reflexive, transitive, and anti-symmetric. And there's just some definitions here, but it's in general pretty intuitive. This binary relation is arbitrary. It depends on how you define it. So for instance, a subset relation is a partial order. And something is an upper bound for a set if basically within that partial ordering, everything in that set is less than that thing. And then you have this concept of a least upper bound and a greatest lower bound. So a least upper bound, for instance, just means that every other upper bound is greater than that upper bound. So why do we talk about partial orders? Because we want to look at these structures called lattices. So a lattice is basically a partial order in which every pair of elements has a greatest upper bound and a greatest lower bound. So you can think about this in general, in a general partial ordering, different things might have different sort of, you can think about them as common ancestors and common descendants. So basically a lattice is basically a partial order in which every pair of elements has this property. And a complete lattice is one in which every subset has this property. So let's get to an example. So for instance, we might want to find out in this program, what are the possible signs of integer variables and expressions at each point in the program. So then we define this partial ordering. So we define these states, starting with unknown sign, and then we have positive, negative, and 0. And then at the very bottom, you have basically this is either not an integer or just unreachable code. And this sort of diagram shows the partial ordering with the edges being just the binary relation. And so in this example, we've defined our binary relation here as basically this thing is at least as precise as this thing. So knowing that something is a positive integer is like at least as precise as not knowing anything about it, for instance. And you can see this is a complete lattice because everything has a common ancestor and a common descendant. So how do we apply this? So we create a map lattice. Basically, this map lattice is just like a mapping between each variable and their sign. And like this sign is just the abstract state that we had earlier. And you can see that like just in the same way as the ordering that we had for the signs formed a complete lattice, this map lattice is also complete, because if you just do a element-wise comparison between each of the signs for each variable, you get an ordering that way. So you create this mapping for each line in this program. So in this example, we just have a very simple program that there's no branching, there's no control flow, it's just 4 lines of code. So here what we can do is we can just create a mapping for each line in the program, and this mapping just maps each variable in the program to their sign. And you can see that there's some dependencies here, right? So like, for instance, in the third line of the program, the sign of B depends on what the sign of A was in the second line. So then, what you can do at this stage is we have this mapping for each line in the program. We can extract this sort of dependency logic by creating a function for each line of the program that returns the mapping, right? So these functions will take in all of the other mappings, right? The mappings for each of the other lines in the program, and they return a mapping for that specific line in the program. And so we now have a generalized equation with basically this is a system of equations at this point, and what we can do here is this is like, because each variable corresponds to the function that returns that particular mapping. When we combine these functions into one massive function f that takes in x1 to xn, and just what this big F just does is it applies all of the little f's to x1 to xn, and so because of what we have above, that just reduces to x1 to xn. So here, like, this becomes a fixed point problem. Like, we're just solving for x equals to f of x. And the nice thing about fixed points is that you may remember, this tells us that there is always a unique and most precise solution, because in a complete lattice, as long as your function is monotone, there is a unique least fixed point. And in this case, our function is monotone because the more that we know about the signs in this program at one point in the program, the more that we know at the next point. So I guess just by definition of fixed points, then you have an algorithm for solving these sorts of equations, right? By definition, something is a fixed point when it doesn't change when you apply the function again. So just by definition, this is the algorithm for finding the least fixed point. But this is very inefficient because you can see that, like, in the dependencies that we had earlier, well, like, the fourth line is going to be dependent on the third line, but like the third line does not depend on the fourth line. So we're doing a lot of like wasted work here because like we're applying all of the functions regardless of the dependencies, and we'll see a more efficient way later. But this does give us like what we can talk about in order to sort of understand data flow analysis. So again, like, we're trying to find the possible values of variables at each point in the program. And this is not just useful in security, this is actually mainly useful in compilers because you can use it for optimizations. So for instance, a compiler might do this optimization called constant propagation, where if this variable isn't going to change, well, you just replace it with a constant. And by replacing it with a constant value, you don't have to look up the variable value at runtime, and that's a nice optimization to have. But in security, well, we're going to be interested in again, like untrusted data reaching a sink. And so if we can talk about what the possible values at each point in the program is, we can talk about whether or not untrusted data will ever reach this point in the program. So in general, like we had a very simple, nice example earlier with no control flow, no branching, but in general, programs do have control flow. So you have this thing called a control flow graph, and basically the basic blocks are just points in the program, and the edges represent the sort of branching behavior. So we had like this thing where each element in the lattice is a mapping between variables and signs. We have the same, we do the analogous thing here, where instead of just having one sort of mapping for each line in the program, we have one mapping for each CFG node, and we call this thing the constraint variable. And so basically our abstract state for this entire program is just you have n of these mappings for n CFG nodes. And in general, when we want to analyze the program at one point in the CFG, well, we have to look at what happens before that. So we have this thing called a joint function. So basically, what this means is that when we reach the point, for instance, a equals to c plus 2, well, what is the sign of c plus 2? Well, that depends on the predecessors of this node. So in this example, this is pretty easy to analyze. So for instance, so your join function would be basically the least upper bound of the previous two nodes. And so in this example, when we get to c equals to b, for instance, we know that we took the branch, b is greater than 5. And so b has a positive sign, and so assignment of a positive value to c means that c has a positive sign. But on the other branch, well, we don't know what b is, because b could either be a positive number less than 5, or it could be negative. But we know that c is minus 5, so c is negative. And so now the join function for this a equals to c plus 2 node, it takes the previous two nodes, the predecessor nodes, and it does the lowest upper bound. And so, well, in this case, so you take the join of b, which is joining plus and not knowing anything about it. And so in the end, like the join is just not knowing anything about it. And so c is either positive or negative. So when you join those two together, well, you don't know anything about it. And then so like the sign of a, well, that's the result of evaluating c plus 2 with the context given to you by the join function. So the join function tells you that you don't know anything about b and c, and so evaluating c plus 2 with that context tells you don't know anything about c plus 2. And so you don't know anything about a, and so here we don't know anything. But this is, I guess, like hopefully you can see sort of like the point here, that we're like sort of using these like dependencies and joining them together and like trying to find out like at each point in this control flow what values things can take. And in this case, of course, we're just analyzing like signs, but this could be extended to a whole bunch of other things. And so, same as we did before, we combine these constraint variables, and we create this like big F that applies all of the little f's. And like, yeah, so again, like we're looking for a fixed point, and this is a fixed point problem. And so here's a more efficient algorithm, a slightly more efficient algorithm than what we've seen before. So the insight here is that most of these functions will only read variables from a few other functions instead of the entire CFG, right? Instead of every node in a CFG. So you have this dependencies array, which is just a set of nodes. So the dependencies of VI is a set of nodes that depend on VI, and those are just the successors of VI. And so you have this work list W, which starts with all of the nodes. We want to process all of them at least once. And so we keep doing this thing where, so we apply the function for that specific constraint variable, and if the result is different than the input, then we haven't found the fixed point. And so we're going to add all of the dependencies for that node into the work list. And so this saves work compared to the previous algorithm, because we're not redoing things when they don't depend on what we're doing right now. And so, well, now we have data flow analysis. We do this thing called theme tracking. So can we tell which computations may involve tainted data. So this means data that comes from an untrusted source. So for instance, you might say user input is untrusted. HTTP responses are untrusted because the server isn't owned by you. And environment variables may be untrusted, for instance. Well, the approach is actually similar. So you just have to define different abstract values and equations. So again, like in the sign analysis example, we had the abstract values as like plus, minus, whatever. Here we have this taint values, which is just like unknown taint status, tainted, untainted, or just unreachable code. And again, you define an ordering on those, and then you have and then your abstract state for each point in the CFG is just a mapping from the variable to the abstract taint values. And then so now again we have these functions, but here well you call them transfer functions. And these are just like, well, you just have like a huge like switch case of like different operations that are possible in your language, right? So for instance, for an assignment x equals to y op z, well, we're gonna say that if either y or z is tainted, then the result is tainted, for instance. And so like the transfer function just like is just saying that. So like if either y or z is tainted, then x is gonna be tainted. And so in practice, well, we have this tool called CodeQL. It's developed by Samo, a spin-out from the other place, and it's now acquired by GitHub. You could use it in the CLI, or you could use it on GitHub. You can integrate it for free with any public repositories, so that's really nice. So how this works is first, CodeQL will compile your source code into a relational database, and this includes information about the control flow, about the data flow, and like just some other properties about the code. And then you're going to be writing queries in this like high-level, like declarative language called QL, which is executed by the CodeQL engine. And then this engine just does what we have been talking about earlier, and just applying fixed-point algorithms to perform data flow analysis. So the results are going to be exported into a standardized format, which you can use in your custom integrations to consume them and report them in whatever like other integration you want. So that's really nice. So, well, let's go on a little adventure. So I was trying to find a demo for this talk, and so I thought, like, why not try to find some actual vulnerabilities of CodeQL. So this thing has been annoying me for quite a while. So some of you might know Next.js is like the most popular like React framework for web development. It has some like really weird and poorly documented URL parsing semantics. Like for some reason, like it does not conform to widely accepted URL standards that are used in the browser, even though it's a web development language. So this results in a lot of unexpected behavior, and a lot of people validate URLs wrongly. I told them about this a year ago during my summer internship, and like it's still not fixed. So well, let's try to find some instances of this bug appearing in open source projects on GitHub, right? So the nice thing about CodeQL is that, like, well, it's part of GitHub. Like, they let you use it for free on any GitHub project. So how does this bug actually manifest itself? So a common design pattern in websites is you might have a link in your bookmarks bar, and like it goes to like some sub-page of a website, right? Like maybe the admin page. But your session has expired. You last logged in like a month ago. Your session has already expired. So when you follow that link, you have to log in again. But then what the website does is that it keeps the original URL that you wanted to go to within the sort of login URL in the query parameters, and then so that when you log back in, you get redirected back to where you were heading before. So you could do this thing because of the way that Next.js handles URLs. You can have a URL that passes like normal URL validations, but then when Next.js processes it before redirecting the user, it turns into this thing that starts with the JavaScript : protocol, and so that allows you to write arbitrary JavaScript code, which is executed on the user's browser. And because this happens after the login succeeded, after the authentication tokens are exchanged, you can steal the authentication token. So, well, let's create a CodeQL query to try to find something like this. So all sort of like taint tracking queries in CodeQL start from something similar to this. So you're going to implement a configuration, and the things that you want to override are isSource and isSync. So isSource tells CodeQL what things in the program are considered like untrusted user input or like untrusted input in general, that you treat as like sources for like dangerous things, I guess. And like isSync is just like you want to find, because you're trying to find like instances where untrusted data reaches sensitive sinks. So isSync would determine what parts of your program you don't want those untrusted data to reach. And then after that, you write like this like sort of almost like SQL-ish statement that you're saying like, oh, I'm trying to find all of the sources and sinks for which there exists a path from source to sink. And then I'm going to output that, and then I'm going to output that string with like the links to like the parts of that code. So isSource, these are some general like predefined like sources that you can have. So remote flow sources like user input, for instance, in the browser's URL. Client request is results of HTTP requests that you make. But in general, because you're in general going to be using CodeQL in your CI pipeline, you might want to extend this with custom logic. So depending on how your code base is, you might have like custom RPC calls, deserialization, whatever, that you want to add into this isSource. And then isSync, well, this is just, we're going to say here, so how this works in Next.js is that like useRouter returns a router instance, and then when you call router.push, that redirects the user, and it does all of that like weird, crazy like URL passing thing, and then before it redirects the user to that page. So what this part is saying is that, well, a node is a sink if it is true that there exists a call and a receiver such that the call invokes the .push method on the receiver, and there is an invocation somewhere in this code that the invocation is the invocation of the function useRouter, and there is a path that takes like 0 or more steps that goes from that invocation into that receiver. And then the node is the first argument of that call. If all of that is true, then that node is a sink. So essentially, we're finding instances where people are using router.push on untrusted input. And also you might want to change the transfer function. So we talked about transfer functions earlier. You might want to extend the taint steps. So like, for instance, like CodeQL might not know about like certain properties of your code base or certain properties of your language or like third-party APIs. So what we're doing here is very simple. This is just saying if the element that you created the array with is tainted, then the array is tainted. And then the second thing here is saying that if your array is tainted and you're calling some of these like functions, find, filter, blah, blah, blah on that array, then the first argument of the callback function is tainted as well. And you can also implement isSanitizer. So this would just say that if this node is DOM-purify.sanitize, then like basically everything after this node is going to be treated as untainted, because we're making the assumption that like everything that goes through this sanitizer is going to be safe. So what I did was that I went on grab.app and then I tried to find, well, who uses a bunch of useRouter calls, and so I found so interestingly Supabase. Some of you might know what Supabase is. It's a very popular backend solution. It's basically meant to be an open source replacement for Firebase, and it has like 80K plus stars on GitHub, like very popular. Every startup nowadays uses it. So then I basically ran that query that we wrote earlier on the Supabase organization, and so I found that there is a call here that's pretty interesting. So I'm gonna do a demo. Yeah, so you can see in VS Code, there is a CodeQL extension. So this is the query that we wrote earlier. Like it's a very, very simple query. And like, yeah, we ran through this earlier. And so when you run it, CodeQL gives you the results here. Let me see if I can, yeah. So CodeQL gives you the results here. And you could see that like, basically, the very powerful thing about CodeQL is that, like, so for instance, when you first look at this, you might say, well, what's actually inside get returned to path? Like, this tells me nothing at this point because how do I know that this is actually untrusted input? So because we've essentially found an instance where untrusted user input from the source goes to a sink, CodeQL is able to tell me exactly where that source is. So it told me here that the user input first came from this part, get returned to path, the first line of this function, which takes the location.search, which is just the query parameters, and like, yeah, it found basically the return to parameter. And so when you just analyze this function a little bit more, like, yeah, it tries to do some validation here, but because Next.js doesn't follow the same standard as the JavaScript URL constructor, like this validation doesn't work. So basically, what you have is that if your friend were to send you this link and you click on it, yeah, so you can run like, basically your friend has just ran like arbitrary JavaScript on your session, and they may or may not have stolen your session cookie. So that's obviously very bad. I'll report this to them, responsible disclosure after this. But yeah, this is pretty cool. So like, this is essentially what you're doing. So like, this is basically what the URL was. And because like, there's some like weird like dynamic routing thing that like Next.js does some substitution on. It passes the normal URL validation because this just looks like a relative path, but when Next.js does its like magic, it strips out the front part. So yeah. And like I wouldn't have been able to find this without CodeQL because obviously like the code base is like several 100,000 lines long, and like you wouldn't even know that like Supabase is doing this in the first place if you weren't able to run these queries at scale. Yeah. Yeah, so there are some limitations with CodeQL. So like it's obviously like a very nice tool, a very nice integration to catch security issues early in the development process. But it's kind of really hard to get right. So you need to create custom taint specifications for third-party library APIs, for instance, because well, CodeQL doesn't know about Next.js, and like I had to write some like very like simple queries for it to actually pick up like what we talked about earlier. But you can imagine like if you have like a very big project and like a bunch of like other like dependencies, well, how would you catch like things that come from like all of these like third-party libraries? So that's a huge challenge, and like that just requires a lot of understanding of your own code base and like writing your own rules to like sort of tune that down. There's also a lot of false positives. So if you're not careful, you can actually like write a query that returns a bunch of results, and like most of them aren't going to be useful. So like there's a lot of effort that's required over there to like just write a query that is like specific enough, but also like not too specific, that like you kind of like catch most things that you want to catch, but also like not too many false positives. And so like you really do need a good understanding of the code base and the problem domain. And so there's a lot of like effort required to get good results, and it's only going to be as useful as the queries that you write. There are some alternative approaches. So there's this thing called symbolic execution, which basically just means that, well, it's a sort of different thing than what we're doing here. It's basically just saying that like, I'm gonna check all of the possible paths through the program, and I'm gonna like generate constraints on inputs that is required to be true in order for a certain path to be taken. So we might say that this path is only ever taken if x is greater than 5 and y is less than 10, for instance. So there's also like some research I saw that so again, the main problem with CodeQL is that like you need to fill in the gaps of knowledge, like when you're using third-party libraries, and like when you have like code-based specific patterns that you want to encode into your queries. So people used LLMs as like an intermediate step, so like you have the sort of pre-processing done by CodeQL to compile the stuff into like a relational database, and then like they use an LLM to sort of like fill in the like taint steps, and then complete this entire process of like the remainder of the CodeQL algorithm. And this like sort of like gave some pretty good results. So these are my references. I think the first one it's pretty much a textbook at that point, like, but it's like really, really useful if you like want to learn more about like the specific like theoretical things that we talked about earlier. So yeah, I hope this was useful. I'm happy to take any questions.
Right, thank you very much. If anyone wants to know more about lub-preserving transforms, continuous monotone fixed point iterations, do denotational semantics next year. If you want to see this sort of stuff applied to compilers, do the Optimizing Compilers course next year. It's probably the best one in the Tripos. Does anyone have any questions in the room? Bloomy, yes.
You noted that for some of the vulnerabilities that CodeQL can discover to be exploited, certain additional conditions need to be met. Are there any particular conditions in a broad sense that are common, and are there any ways of finding out what those are?
Yeah, so I guess like, for instance, like this whole like URL parsing bug that we mentioned earlier, like one very simple example could be that if their Next.js version was just so outdated that they didn't have this weird thing introduced in the first place, then this just wouldn't be exploitable. But in general, like you need to take in like context such as what library version are they using? Do they have any like custom sanitizers in their program? And like all of these things, you only really know if you're the one that's like writing the program. So that's why like CodeQL is like, I think it's mainly useful if you're trying to implement like this pipeline in your own like software development like cycle. The way that I used it here, like trying to find vulnerabilities in like open source projects, you can use it that way. It's just that like you're probably going to get a lot of false positives because of these like other things that must also be true in this world in order for this thing to be exploitable. And yeah, like even this query that we wrote, like there were like some other like false positives as well. So for instance, like you had to have control of the entire URL. So there might be some results where you are able to control like maybe part of the URL like after the first character because they do like a / plus like your user input. So these things are just like, again, like it's really hard to like sort of nail down, and you have to like write like queries in a very specific way in order to like reduce these like false positives. So I hope that answers your question.
Yeah, it does. Thank you.
Thanks for the talk. I was wondering if there are any like projects that are applying this kind of data flow analysis to compiled binaries, and if they're used to find vulnerabilities in a similar sense to CodeQL is on a source code level.
Yeah, I think there is some research on this. I don't remember the specific name for what they called it. But yeah, like in general, like like I think what most of this research does is I think because it's still like, if you're doing it at like the actual like binary instruction level, like fully at the binary instruction level, like that would like take a lot of, I mean, like it would be like too big. But like what some of them try to do is that like they do like some like very basic like decompilation to try to identify, for instance, like map like decompilation to map like certain parts of the code to like a loop, or like a like just like some like C like code, and then they try to do this thing. But yeah.
I see. Thank you. That's interesting.
Any other questions in the room? Great. Thank you very much.